Suppose we place a bar of zinc in a solution of copper 2 sulfate. Over time, we observe that a redox reaction occurs. There's our bar of zinc. There's our solution of copper 2 sulfate, which is a deep blue color. And over time, we observe that some of the zinc is eaten away, and it's now coated with copper. Perhaps some copper is even sunk to the bottom, and the solution is no longer a deep blue color. It's either colorless or a very, very light blue. And that's because there are a lot of zinc ions in that solution now where there weren't before. So what's happened here, you can see on the left, is we've had zinc be oxidized to zinc ion, and we've had some copper 2 ions be reduced to form copper. I'll show that on the right side as well. The net reaction here is that zinc has been oxidized to zinc ion and copper 2 has been reduced to copper. This is important. No useful work or energy can be harnessed here because the electrons that are transferred go straight from the zinc to the copper 2 ions. And if we want to harness some of that energy from the electrons, we have to sort of get in there. And if the electrons go straight from the thing that is oxidized to the thing that is reduced, we haven't really gained anything by the movement of those electrons. In line notation, we would write, of course, the oxidation reaction shown on the left, zinc being oxidized to zinc ion, and the reduction reaction shown on the right side of the double line between copper 2 plus and copper. Here you get a much better feel for what's happening because I've got photographs of the before and after. You can see before we had the zinc in the copper 2 sulfate solution, and at the end we've got some solid copper that is coating the zinc, and you can see how the color of the solution is much less blue. This reaction, as we noted, takes place spontaneously, which means we set it up and it just goes. From previous studies of thermodynamics, you recall that the sign of the change in the Gibbs free energy for such thermodynamically favorable processes, which is a fancy term for spontaneous, is negative. If, instead of zinc, we placed a bar of silver in a solution of copper 2 sulfate, so now let's put a bar of silver in there, and there's our deep blue solution of copper 2 sulfate. Sometime later, here's what we will observe. The silver is virtually unchanged. The copper 2 sulfate solution is still a deep blue color. In other words, there's no reaction. And if there's no reaction, the delta G, that is the change in the Gibbs free energy, must be positive. That is, this change is thermodynamically unfavorable. We set it up and it doesn't want to go on its own. We'll get into more about why some things are thermodynamically favorable and other electrochemical reactions are not later on. Here we're just noting that some of them take place spontaneously and others don't. If an electrochemical process is spontaneous, can we somehow harness the movement of electrons to do work? And if it isn't, is it possible for us to make it happen? On both counts, the answer is yes. And to do it, we need to set up an electrochemical cell. We obtain useful work from spontaneous electrochemical reactions by setting up a galvanic or voltaic cell. Those are synonyms, a galvanic cell or a voltaic cell. And we can force non-spontaneous electrochemical reactions to go by setting up what's called an electrolytic cell. In short, some electrochemical reactions will go spontaneously, and if we want to use some of the energy that is transformed in such a spontaneous process, then we need to set up what's called a galvanic or a voltaic cell. Other electrochemical reactions do not happen spontaneously, and if we want to force them to happen, we have to set up what's called an electrolytic cell. These are subjects for future lessons.